Okay, so orthogonal projection on a vector line. Let's have some kind of representation in R2. So, or R3, by the way, it's just going to work very, very similarly. Right, so you've got R2, let's say, the plane, and you have a vector line. So it's a line that has to go through 0, and let's say that it has direction vector A, right? So my direction vector of my vector line, right? So my line, you can also write that my line is the span of A, all right? Let's say you have now an element, let's call that B. That's my B element of R2, so you know it defines a vector, so that's my vector B. And I want to find, well, there are several ways to present that. What we want to get is actually the orthogonal projection of my vector B on A, right? So that would be the element, that's called that PB, the element of my vector line, that would be, well, we could say the closest to the vector B, but that belongs to my vector line. And, well, it's going to be given by this orthogonal projection. Why? Just simply by Pythagorean theorem, okay? So you clearly see that that element here is going to be the closest to my B element, and the closest point to the B that belongs to that line. All right, there's just by Pythagorean theorem, right? So I'm looking for that PB, right? So PB that belongs to the span of my vector A. All right. I know that it belongs to the span of A, so I know that my PB can be written as some value x times A, right? That's exactly what is written here. All right, there it's equal to some value x, so x is a real number, and A is an Rn vector, and PB is an Rn vector. All right, so that's one thing. On the other hand, I know that, as I said, this is going to be a right angle. So, and that vector here, it's PB minus PB. Okay, right? So, why? Just by Charles' theorem, right? The sum of B plus, well, depending on what direction I take it, but B minus PB would be this one. Okay, so the sum of P plus B minus PB goes to B. That's just Charles' theorem, right? So, and what do I know about this vector? I know that B minus PB, or PB minus B, it's just the same, is going to be orthogonal to A. All right, so what do we know? We've just said that that means that the dot product of P minus PB with A, so that's a dot product that's going to be equal to 0. And, well, one of the notation, using the matrix multiplication notation, that gives me that the A transpose vector, so the row vector A times B minus PB is going to be equal to 0, which I can expand as A transpose B minus A transpose PB is equal to 0, which of course I can rewrite as A transpose PB, this is what I'm looking for, is equal to A transpose B. And as I'm looking for, and I know, that's what I said earlier, that my PB was equal to x times A. I'm just going to substitute PB by x times A, but as x is just a real number, I can rewrite this as x times A transpose A, and that should be equal to A transpose B. And finally, I can find my x value. It's just going to be given by ATB divided by ATA. Okay, don't forget that A transpose times A, that's just the norm square of A. So let us see what we have now for the vector P, B. PB is just going to be given by x times the vector A. So according to what I have above, it's just going to be AT times B divided by AT times A. And of course, as we said earlier, the x, well, the whole stuff times A, sorry. That whole coefficient belongs to R. Okay, that's my x. Okay. So I can also write this as being A times ATB over ATA. And this is very interesting because what we have here, so that's PB. This is really written as, so my vector PB is this thing times the vector B. And what is this thing? This is a matrix of size, well, n times n, if B is a vector in Rn. Why is that? The bottom here, that's a real number because that just equals to the norm of A square. And the top here is going to be that one, that's the vector A, column vector, times A transpose, so a row vector. And so the result of this multiplication is just going to be an n times n matrix. Okay, and so I can say that if I put that capital P is given by this matrix, this is your projection matrix on the vector line A. Okay, and this is what we have described here in the lecture notes. You've got all the calculations and also this way of writing things, which I personally like, because, well, we have B dot product with A or with a normed version of A. That's interesting. That's the same vector as A, but with norm 1, so indicating the direction, but with a norm 1. And so you take the dot product with this norm 1 vector of B and multiply by the norm 1 vector, and you get exactly what you expect. I mean, exactly the what you would also find using some geometric reasoning with the cosine and the norm of A, the norm of B description of the dot product. Okay. So this is also all the calculations are reminded here. Okay, so we can make our calculation our projection matrix. And the interesting thing that we can add about this projection matrix, what's happening if I square this? Okay, let's write this. A transpose over A transpose A times A transpose over A transpose A. What is this? What do you think is that? Okay, so that's going to be, so we've got A transpose A, that's going to be here. So it's going to be simplifying with this, and this is going to be A transpose divided by A transpose A. What is that? That's exactly P. And actually, that's something we will study later on, that this is one way to describe projections. If you apply your projection twice, well, you just stay where you were, right? What is the closest vector from that vector line closest to any point of that line? It's just going to be any point. It's just going to be itself. Okay, so that's it for the projection on the vector line and the corresponding projection matrix.